Okay, hello everyone. It's the third day of SIGMOD 2025 conference, and also it's our third presentation and share of paper podcast in SIGMOD's PODS 2025. And today it's such honor that we have the speaker. Actually, we have two speakers today. I would introduce the first. Deng Yangshen. He's a master student in database research group at the Southern University of Science and Technology, and also a co-founder of AnalayaDB. Actually, it's also already the last year of his master study, and in this September, he would begin his PhD study in University of Edinburgh. Right? Yeah. Okay. Actually, Yangshen had so many research experiences, such as in University EPFL, also University TOD. Let me try to pronounce it. It's a Technical University of Dahastma. You can correct it later. Okay, Yangshen focuses on the database systems and AI system research, and he already published many papers in top-tier conference, including the SIGMOD VRDB and SOCC. He has his own personal page, very easy to Google. So if you want to check more details, just Google the name. Okay, I will let the speaker Deng Yangshen have the mic. So let's welcome. Yeah.
Thank you, and hello everyone. I'm Yangshen. So I'm a master student from Southern University of Science and Technology, and also the co-founder of AliaDB.ai. And today, the topic I want to share is architecting the next generation data systems in LLM era. And this is what we, AliaDB.ai team, are now trying to do. So what do I mean, the next generation data systems? So let's see nowadays what people are doing in the traditional database world. So we know that we do transaction processing, OLTP, and we do analytical processing, OLAP. But now we are trying to propose a new concept called generation processing. So what is generation processing? This is our definition that we try to use the vector similarity search operations to generate better answers in the LLM era. And so we, AliaDB team, is a team that's very good at vector search, solving vector search problems and building vector databases. And we are trying to do these two things. So let's see large language model as a function f, and x is its input text and or images or something, and y is its generation contents. So the first thing we do is we are building a vector database and RAG framework for extreme performance called Alia Lite, and you can check it is open source, and you can check this code and reproduce the experimental results. And the second thing we are trying to do is to utilize the vector search techniques to accelerate the LLM inference. And this is a totally new vector database architecture, and this is the paper I want to share in this talk. So this is the title of the paper, The Data Foundation for Efficient and Effective Long-Context LLM Inference. And me and Zhenxin and Long, we are three co-first authors, and we are all students of Professor Bo Tang in the school. And this is our AliaDB team. As you can see that more than half of us are here in Berlin. So if you are interested, you can talk to any one of them. They are all in our team. So let's start the AliaDB introduction. So what are database guys doing in the LLM era? So we know that the LLM can help, we can do AI for DB. We can help do help improve the query optimizer, do text-to-circle, and do data engineering jobs. And we can also do DB for AI, which means we build racks or we build data cleaning pipelines or something like this for to enhance the performance of large language model. Instead of these two types of databases, we try to build a database inside the LLM. So what is AliaDB? So it is a vector database in LLM, and this is the two functionalities. The first is it do KV cache management, and the second is it do attention computation. And in such a way, it can support long context LLM inference with low resource, low latency, and high quality. So, what is long context LLM inference? It means your input is really long, and it has a lot of application scenarios like long document analysis, code analysis, and chatbot with long chatting history, and so on. And let's take this example that this is a book that the textbook that we may all know, and it is it contains very much many pages, and we ask a question about this book, which means we input this book and this question into LLM, and this is what we caused. If we use a model, the 8B model, and we will cause two NVIDIA A800 GPUs to run for 6 minutes. This is very expensive because you only ask a very short question. So why is it expensive? So this is, to answer this question, I have to introduce some of the LLM inference basic knowledge to you. So this is how it works. We input our questions and our context into the large language model, and it will generate the token one by one, just like this. Then the second time we input a context with the generated token and do that again and again. So inside the large language model, we have a lot of neural network layer, and the most important layer is the attention layer. So how did it do? So what attention layer do is that it accepts a lot of inputs. For each token, you have one vector as the input and output, and one vector as the output. Let's see how it works. So for example, it will for each token, it will have 3 vectors called Q, K, and value. And for one token, let's see the DB token, the query vector has to do attention with all its contexts called K1, K2, and K3. So it will first do an inner product with all the keys, and after that, it will go through a softmax layer to get our attention weights, and then this weight will be applied on the value vectors and gathered together with a summary. So in this way, it will generate its vectors and have a grasp of the overall context that is previous to it. So in LLM inference, there is 2 stages. The first stage is a preview, as we can see that if we do the operations I mentioned before in parallel together with all my inputted index context, then this is preview and it can be done in parallel. However, in decode, we have to do it one by one, so this is the decode stage. We will do the attention only for the newly generated token. And this part, our context part, the key and value will be cached in the GPU memory or something. So that, and in this case, we call it KV cache. So what is the challenge of long context LLM inference? The first thing is we have very large KV cache. For this book, we will have 141 gigabytes KV cache. And it's very large, especially for the GPU memory. And it has heavy attention computation because we have to do such a computation I mentioned before, and it costs a lot of time for even 6 minutes for this simple question. And in previous works, there are a lot of works in the system community and AI community to to solve this problem. And the opportunities lies in, for example, for the large KV cache, Kimi and Mooncake, they will try to offload this KV cache of long context to a disaggregated system so that we can improve the reuse opportunity of it. And the second, for the heavy attention computation, people found that we could do it sparsely instead of do a full attention so that we can reduce the computation intensity. So this is an example of the sparse attention, which means it is very intuitive because this is how humans read a text. For example, when we read a context, we will only focus on a few part of it instead of go through the whole book again. So this is the same in the attention. For example, for this token it, possibly it will only focus on the DB word instead of the other words like what and is. And in this case, from the mathematics, the key 3 will have larger attention weights to the Q5. So this part will contribute more in the final output. And in this case, we can only focus on a few tokens, but generate the context still with the high quality. So here is the question, since we already have a lot of research work on it. So are existing systems or algorithms good enough? And the answer is no. We try to summarize the existing works into different architecture. The first architecture is the cardboard architecture, and like the SGLang and VLM. So they will manage and reuse the KV cache in GPU. And this framework, they will do model inference, attention, and context together in a whole monolithic architecture. And they will do full attention. So in this case, and because of the high computation intensity, the latency is high, but the quality is good because of the full attention. The GPU memory consumption is large, as we mentioned before. And these systems are very easy to use. So very simple interface. And the second is the KV cache disaggregation, like Mooncake and LM cache. And in this case, they try to maximize the reuse possibility by offloading the KV cache to a storage service. So they disaggregate the KV cache management from the inference engine. And in this case, the latency will be slightly reduced, but the GPU memory consumption is still large, and they are, for my knowledge, and they are not easy to deploy. So the usability is not that good. And the third thing is the retrieval-based sparse attention algorithm. So what they are trying to solve is to reduce the computation and also the GPU memory consumption. So they will offload the KV cache to CPU, to a KV cache store, and they will retrieve the parcel cache, KV cache, the important KV cache for attention, and they will retrieve the KV cache into the GPU and let the inference engine do the sparse attention and the model inference work. So there are a lot of algorithms here, and most of them are, each of them are the trade-off between latency and quality. So for this algorithm, if you want higher generation quality, the latency will be high. So that's why we don't summarize the latency, and the quality is not that good. And however, it can significantly reduce the GPU memory consumption in long context inference. And in terms of the usability, they are very hard to use because most of them are research work, and it lacks a framework to integrate all these of retrieval-based sparse attention algorithm. So, for example, if you try to switch to another new model, then you wouldn't be able to use the code from its repository. So this is summarizes of the existing architecture, and here this is our goal, and what we achieved by using the vector search, using the vector database for LM inference. So for AlliaDB, it has low latency, good quality and small memory GPU consumption, and even very good usability, just like the coupled architecture. So this is the new abstraction we proposed. So instead of, this is a new disaggregation level that we decoupled not only the KV cache, but also the attention from the inference engine and encapsulate them into a vector database. So in the vector database, they will do something like the retrieval-based attention algorithm, but in a more, in a better way. So it will still retrieve partial KV cache for attention, and it will utilize both the GPU and CPU memory to to do the attention together. Yep. So this is our motivation. Is that well, very simple. That we try to seize the opportunities for LLM inference with database techniques. So what do they mean? The first challenge, the first opportunity is called storing and reusing the context. Is actually storing and reusing the vectors, because this is what KV cache is. So that we can store it via a vector storage engine. And the second thing is the sparse attention. And the sparse attention itself is actually something like the vector search problem, so that we can find a way to do that with a vector search engine. And interestingly, these two things, the vector storage and vector search, are the two things what database community is really good at. So this is also an opportunity for the whole community. Here, let me first introduce the architecture of the AlayaDB. So we have a user interface, very simple abstraction, only with session and DB. And then we have query processing engine. It has a fast attention engine and a novel query optimizer for choosing the best sparse attention algorithms. And underlying, we have the vector storage engine, and it is mostly based on our vector storage engine of the Alaya Lite database. So first, let's introduce our interface and API. So the session is our abstraction that stores the states of an ongoing context. So and it is compatible with the KV cache class, the dynamic cache class in Hugging Face transformers. And it has a method called attention, and this attention method is compatible with the flash attention, which is the standard, currently the standard of the attention library. So this is an example. If you try to use AlayaDB for transformers, you will only have to change two lines of code. That replacing the first, you replace the key value KV cache with the session class, and the second, you replace the flash attention with the session.attention. So next, let's introduce our magic, that why we can do even better than the existing retrieval-based sparse attention algorithms. Here we propose a vector search query, DIPR. And so let's get back to the sparse attention part. So the challenge of the sparse attention actually lies in how do we quickly and accurately locate the tokens with high attention score here. And actually, it is actually a maximum inner product search problem, a very traditional vector search problem, because let's see the formulation. What we actually want is to retrieve the keys with high inner product value to our given query vector. So previous methods, just like what we did in database community, they use top K query to handle this problem, which means you set a case statically, and each time, no matter for which layer or which context, you will retrieve, for example, the top 100 tokens. However, we found that for attention computation, there is limitation. Because it does not match the goal of attention approximation. So what we do here is not trying to get a the top 100 or top 1,000 important tokens. We actually are trying to approximate the attention by our selected tokens. So the top K, it focuses on the ranking. However, what we want is we want to focus on the score instead of the ranking. So, so this is the limitation of the problem itself, the top K problem itself. So, and we found that first, we have two observations. The first observation is that we found that the number of critical tokens is dynamic in hash. And for example, here we shows the so we shows the how many tokens do we need in each layer and each head, so that we can get a recovery ratio, which means the approximation, a good approximation of the full attention. So we found that for each layer, the number of critical tokens we need are really different. And the second thing is we found that different tasks itself also needs different number of critical tokens, and this is different tasks. We found that, for example, for the complex tasks that we need to do, for example, summarization and multi-hop inference, we need a higher proportion of critical tokens. But with the trivial tasks like trivial QA, we only need a very small K. So the question is, can we design a new vector search target so that we can beat this dynamicity and it can be searched efficiently? The answer is we can. So this is the new vector search problem we proposed. First, so the intuition is we try to use the largest attention weight as the pivot, and we try to drop the attention weights that are too smaller than the largest one. So this is the formulation. The Aij is the attention weight of an token, and alpha is a constant that we proposed that we can define by our own. So we are trying to drop the attention weight that are smaller than the alpha times of the maximal attention weight. And interestingly, this formula can be transformed into a kind of range query on the inner product space, just like here. So in this case, we try to find the vectors that has an inner product value that is larger than the max inner product value and minus a constant beta. So this is an example that if we set a beta to, for example, to a proper value, we can approximate this one. Like these two lines will be, I think it lacks a line, but the blue lines will be very close to the wave of the red line, so that we will not waste a lot of computation, and we will retrieve all the important tokens. And this is an experiment that shows that for different tasks, and the DIPR target can, with the DIPR targets, we can have higher accuracy with smaller number of critical tokens retrieved than the top K. So, so after we introduce the target, the next question is how we do the search. So the challenge of the DIPR search, so what is different from the range query in traditional vector search is that the maximum value is unknown. So this is the dynamicity. So which means if we are traversing through an index like the graph index, we must not stop before the maximum value is founded. And the number of required points is unknown because it is not top 100 that after we find 100 tokens, we can stop. No. So we want to find all the tokens within this range. So which means we must coverage and stop after the required points are founded. So this is our proposed simple and very efficient DIPR search algorithms on graph index. For this algorithm, we will first set a capacity threshold of our candidate list. And if our candidate, the capacity of if our candidate size is less than the capacity, we will try to explore every node. So this is to ensure our pivot tokens can be found. And after the candidate is expanded to larger than the threshold, we will explore only the critical tokens. So this is how we try to ensure the convergence. So here's an example. The figure A is an example that the candidate is small. We will try to append the nodes that is actually not with so large in a product value. But after that, after we have 3 candidates here, we will only append the blue nodes, which has the high in a product value. So so based on the DIPR, we also have a query optimizer that we found that DIPR or no matter DIPR or top K, they are not always perfect in all the case. So we summarize this, we propose a framework that we can unify all the sparse attention algorithms into coarse grain index, fine grain index, flat index, and also different types of query methods. So in this case, we can integrate the new sparse attention algorithms and integrate our optimization knowledges. So for example, here is an optimization workflow in our optimizer. We will try to select the best sparse attention algorithms according to the layer, the head, and also the hardware resource you got. And furthermore, because we are trying to build a product, so we have many end-to-end optimizations, and we don't have time to introduce here. You can check it in our paper. Here, I will give a brief introduction of our experiments. Our experiments are run on NVIDIA L20 GPUs, and we set the SLO to like 4 to 5 tokens per second. And the question is, can AliaDB achieve low latency, high quality, and low resource consumption for long context inference? The answer is yes. So the first is we showed the experiment results in the infinite bench. We found that we have the highest quality under the SLO, and we can even have higher scores than the full attention method. And in terms of the resource consumption, comparing to all the existing methods, we will have the smallest GPU memory consumption under the SLO. And this is the second experiment is about the time to first token SLO. We found that with AliaDB, since you don't have to retrieve all the context into the GPU first, like the mooncake, we will have faster context reuse speed than the KV cache disaggregation architecture. So finally, this is some takeaways of this paper. So the first is that using vector database for LLM inference is actually a powerful way. And the second is some principle of building such a specific vector database, which means the first is if you need to disaggregate the KV cache from the inference engine, you should also disaggregate the attention. And the reason is that if you try to see the attention formula, you will find that attention is actually a near data computation, just like a DB operator. So that, for example, in the future, we can store the KV cache in different storage tier, memory tier, and conduct the attention operations on different machines and then aggregate them together. So thank you, and this is the share of AliaDB. Yep.
So nice talk. Okay, we into the QA session, and first we will later the question changes for the people online and also the offline. So any questions? Any questions? Okay, I got one question from online. Could you share case study where LM optimization database significantly outperform traditional system, especially in complex scenario like multimodal data retrieval or real-time RAG pipelines.
So, can you say that again?
Yeah, you can read it. Yeah, take it free.
Case studies.
This is a question from audience online, and also the people who sit there can. Yeah, if you have questions.
Yeah, so the first question is about the performance of this kind of optimized database in the scenarios of multimodal retrieval and real-time RAG pipelines. So actually, we, for our experience, we focus on the infinite bench, the benchmark for the very long context inference with tokens of about 100K to 200K. So we are trying to work on the modality retrieval, and we don't get experimental results now. And for the real-time RAG pipelines, I think that this is some kind of the methods that is it has different functionality than RAG, because, for example, in RAG, you usually wouldn't have too long contexts. You are trying to retrieve some text chunks to integrate it into not so long context and feed it to the LLM inference systems. But here, we are trying to input all the context into the LLM so that we can get better results than the RAG pipelines. But these techniques are actually can be used together. So that's my opinion of that. And the second problem is that what is the communication, the hardware settings of the database system and the inference system. So here, our database are actually deployed on the same machine of the inference engine, and we also have some experiments now trying to disaggregate them into different engines so that we can have a better deployment. And and we found that the network, because we don't have very good network, and for the network we use, it will sort of affect the latency of the generation throughput. But we've found that because it is actually a storage service, you can actually deploy them on the same machine and expand your SSD and memory and CPU memory to get a very good performance. Yeah.
Okay. Good. Any question? Okay.
Hi, very nice talk. I'm just wondering that if AliaGB is coupled to the DIPR algorithm, or it can generally support any further follow-ups on DIPR, and so the follow-up question is that what is the goal or target of AliaGB? You're going to build it as a dedicated system with a very high dedicated sparse attention algorithm, or you're gonna build it towards a general framework that can support any algorithm and system trends?
Yes, I think that it sounds like two same questions, and I would like to go back to the query optimizer space, and here. So thanks for your question. And what AliaDB want to do is actually a new abstraction and a new framework. So the new abstraction means we have a very simple API, so that and we are trying to standardize it, because if everyone, for example, you can even think that you have one vector database and you try to implement one attention operator on top of it, you can implement our API, then you can be seamlessly integrated with the transformers. So this is the first thing we want to do, that we are building a new abstraction. And the second thing is that we have a framework this is what we do in the query optimizer, so that you can integrate different kinds of the attention algorithms into it and build your own optimization workflow. So this is the second thing we do, is a general framework for this kind of vector database for LLM. Yeah.
Okay, thank you.
Okay, thank you. Any question? Okay, so nice talk. Let's thanks to Deng Yangsheng again. Yeah.
Thank you.
Okay, now I would introduce the second speaker. It's also such honor we have Liu Haotian here. He's a PhD candidate in database research group at the Southern University of Science and Technology. His supervisor is also Professor Tang Bo. His research focuses on big data system, cloud native DB, and also vector DB. And he already published many papers in top-tier conference like SIGMOD, VRDB, and the SOCC. And currently, he also is also co-founder of the AnalyteDB. And also he has open source projects on GitHub, a lightweight vector database. And this open source projects now already have over 100 stars. So it's great. Yeah. If you're interested, check more details. Okay, I will let Haotian have the stage. Thank you.
It's my honor to be here. Thanks for having me. Yangsheng has just talked about how we use a vector database for LLM inference. Now I will share something in low level, like multi-tenant management in cloud environment. Okay. Nowadays, many users tend to rent cloud service rather than deploy their software by themselves. Of course, they have different requirement of performance, that is to say, quality of service. Based on this difference, they will rent different types of cloud services. And also, from the vendor's perspective, they manage multiple tenants, so it provides a chance to increase resource efficiency and reduce costs. And at the same time, they need to guarantee the service level objective for each tenant. Okay, and the most direct way to manage multiple tenants is to encapsulate resources and allocate them for something like database. For example, there are some virtualization and containerization techniques, and they can encapsulate something like virtual machines or containers. And so some data service can be built atop these containers or virtual machines. If we deploy them on virtual machines, it is based on infrastructure as a service. And if we deploy it on container, it becomes a platform as a service. At the same time, there are also lightweight containers, lightweight virtualization techniques for cloud vendors like Amazon Lambda, so that each virtual machine can start at a sub-seconds, and they don't need to load the image into them, so that a database service can be built atop these functions. And of course, there is an inherent trade-off between the consolidation and the performance isolation. In general, the higher the isolation, the poorer consolidation. For example, virtual machines are highly isolated, but the consolidation is lower than these like containers. The major challenge behind this is the fungibility. The fungibility is the ability to resign resources quickly without disruption. Let's consider a scenario where a single database instance that manages multiple tenants. First of all, if there is no interrupt is introduced, the long executing tenants will occupy the CPU and work for a long time, such as the figure A depicted here. And if we schedule the tenants using multi-threading, and so that they can be scheduled by operating system and in the context during the context switch, and it will, first of all, it will incur a lot of context switch overhead, so that we cannot do fine-grained management of them, such as the black bar depicted in figure B. And also, since the operating system, the scheduler of operating system cannot be directly controlled by users, so it is not flexible. So what we do is to follow the idea that decomposition facilitates execution. That is, we decouple the execution of all tenants into fine-grained execution unit. We name it tasklet, so that like the figure depicting C, all users we can do fine-grained control of all tenants, so that the green one and the red one can respond in a faster time. And let's formally define our problem. We focus on the CPU SLO, which is defined by a metering interval and a reserved CPU percentage. That is, for example, if the CPU SLO is 50 milliseconds and 80%, it means that we need to provide 40 millisecond CPU time across all cores for every 50 milliseconds. The 40 is 50 times 0.8. And our solution of this work is to split jobs from tenants into fine-grained tasklets. Specifically, a job is an execution plan in database, and we also name a task as an operator, like a node in this DAG, and the tasklet is a very small slot in each node. That is, the tasklet is even smaller than the task in operator level. Okay. Now, let's dive into the details. First of all, we need to generate such DAG, such tasklet-based DAG. And what is tasklet and what is split? In our work, split is suspended with C++20 coroutine. In many databases, there are function calls. For example, the hash join in A, in left part A, and it will, for example, it will first build a hash table, then prop to get the result. And during this function call, the call stack will be every function call will stack a function in call stack, so that the call stack will be bigger than smaller after the corresponding function finishes. And for C++20 coroutine, it is very similar to the function call, rather than the difference I labeled in red. For example, if we first change the coroutine class return type as warped by coroutine class, then we change the return to co-return, then we can inject co-await like something like yield into our C++20 coroutine. And since C++20 coroutine is stackless, once the coroutine call will not change the underlying stack. And once we inject yield here, and the current CPU that running the current coroutine will are able to execute the coroutine of other tenants. And it is very easy to use. That is, we only need to change several lines of codes if we prepare a well-organized coroutine class and a waitable object. And these things we will discuss later. And since C++20 coroutine is very lightweight, for example, we create it, yield it, resume it, only takes nanoseconds. Thus, we can inject a lot of suspension points so that we can make them in a very fine-grained manner. And we also provide some methods to generate such tasklets. For example, in high-res, that is where our system is based on, it will execute an operator chunk by chunk. Then we can inject a yield point once we just finishing a chunk. And also there are also subtasks such as for example, if something subtask A will do part A, subtask B will do part B, and then this subtask can also be split into fine-grained tasklets. And after this splitting, the execution granularity becomes very low. For example, the median tasklet time is several microseconds, and by contrary, the median task time, that is the operator time, takes milliseconds. And then we have already generated such tasklets. That is, we abstract the code segments by injecting yield point by using C++20 coroutines. Then we focus how to execute these tasklets. Specifically, the problem is how to define the coroutine class and the awaitable. And to address this problem, we first review and abstract how high-res executes jobs. Specifically, high-res execute job in a DAG manner. That is, once we want to execute C, we need to first finish A and B. And there are four key functions. First of all, try schedule. That is, the code logic starts from the top node, that is F, and then E. Then E will invoke C and D. Since for example, both C and D will trigger the execution of A. So, and we should guarantee that only A is executed only once. So we need the function try schedule. Also, we need a schedule function because the A and B and C and D, they can be executed in parallel. And there are also waiting logic and notify logic to handle the dependency in this DAG. And to build this DAG executor, we first analyze the design requirements, and we conclude them into three points. The first one is the isolated execution context. That is, if we have multiple tenants and they have different job, and job is DAG, and the tasklet from different job can execute together without influence, without the influence by each other. If this is the fundamental requirements for us to schedule the tasklets from multiple tenants. And the second requirement is the parallel execution. That is, A and B can be executed in parallel, and C and D can be executed in parallel. And the third one is automatically dependency management. That is, the DAG has an topology order, which is the data dependency, and we need to meet this dependency during the execution. And to address this problem, we abstract four semantics, that is entry, wait, notify, ongoing, and they are similar to the semaphore operations in operating system, but there are also something different because They are designed specifically to execute DAG. And since it is very difficult, I will don't introduce in this talk. And if you are interested in it, you can review our paper. And with these semantics, we can write code in synchronized manner and execute them in asynchronized manner. And then we can just focus on where we should inject yield point, and rather than focus how the DAG can be executed correctly. That is. And after we can execute the tasklets, then we consider how to schedule the tasklet from different tenants. That is, we use a token bucket model to model the CPU SOO. Specifically, CPU SOO is periodically fits the token bucket for each tenant. And we also use a global token bucket that can be to dynamically adjust dynamically catch the idle time during the execution, so that we can adjust the number of active numbers of core accordingly. And why the token bucket model can model the CPU SLO of multiple tenants, because our execution are very fine-grained. That is, remember, we have microseconds granularity of the execution unit. And it's just like water, because water is fine-grained, and then if you put water in this bucket, it becomes the bucket itself. And that is why this system is named Tao. It's from Chinese philosophy, Tao Te Ching, where the great virtue is like water. And then we do some evaluation of our system. Specifically, we simulate two types of tenants with different SLOs. First of all, we simulate 12 TPCC, and we use them to simulate the latency critical tenants, and whose SLO is 50 ms and 50% of CPU. And we also introduce sync time. That is, between every two transactions, each tenant will wait for 50 milliseconds. And we also simulate 12 TPCH tenants. They are used to simulate the best effort tenants, and their SLO are given 500 milliseconds and 50%. And their SLO, their interval is much larger than the TPCC to depict the different features of these tenants. And we also introduce sync time of 500 milliseconds. That is, between two queries, they will wait for 500 milliseconds. And also, we built two service level indicators to evaluate how good we achieved of the CPU SOO of each tenant. And we evaluate the median number, minimum SLI and the median SLI of each tenant with different core provided. Of course, obviously, the red line depicts the performance in tau. That is, we achieve better SL with the same number of cores. And also we can control the resource for provisioned CPU resource in a very fine-grained way. That is, since all the tenants has 50% CPU requirements, the optimal resource utilization is 12 cores, and our provided CPU resource is near optimal because it is close to the gray line. And also we achieve the SL resource Pareto front so that we can use less CPU to achieve the same SLO, or if we want to achieve the same SLO, we only need less CPU core. And since we can dynamic adjust the provided CPU, and since the sync time we introduce sync time, the workload will fluctuate, and we can adjust the resource accordingly. And with this resource adjustment, we can achieve the better worker efficiency, so that our CPU resource can be better utilized. And what the scheduling, we also depict the scheduling procedure inside the TAO. And we know that the blue one is the TPCC tenant, and its execution is like it can always get the CPU. Maybe they are in different cores, and also all of the tenants are executing in a very fine-grained manner. That is 0.001 seconds for each slot, and that is what our system. That is TAO. Thank you very much.
Okay, thank you. So nice talk. So any question here? Okay, I got the question from online audience.
Okay.
So the first question is the source would be open source?
Open source, yes, yeah. we will open source it, but no,
maybe later.
Maybe later, because now it's some commercial reason. I want to open source it actually.
Okay, thank you. Actually, it's also a question for the first speaker. I'm not sure, because the first speaker has to left because he has to give the presentation on SIGMOD at 11 o'clock. And there is an additional question also for him. Is his work another DB gonna be open source?
Maybe I cannot ask it.
Okay, sure.
Okay.
So for this audience, that you can check or connect with the Deng Yangshen. And also you can check the details on the industry paper. SIGMOD industry paper is already released. Very easy to find. Just Google SIGMOD 2025 and plus or not plus is okay. Plus the keyword NianDB. Okay, thank you.
Okay,
that's all for today. And I give welcome again. Thank you. Today we have so nice two speaker and give some how the vector data or how the system resource scaling contributed to the area of the LLM. And I just give you some preview what's in the next 2 days. Tomorrow we're gonna have the talk given by Shanjiao University. And the topic is still about LLM plus DB. And in the last day, we're gonna have the presentation given by the professor from Canada, Carlear University. I'm sure I'm not pronouncing wrong the name of the university. Anyway, in the last day, the Friday, the presentation actually is about the based paper. This SIGMOD. So please. If you're interested, please check, come to our podcasts and check the details, ask a question to the professor, to the speaker. Okay, thank you. That's all for today. Tomorrow and the Friday, the same time. Berlin time, 10 o'clock in the morning, and Beijing time, 4 o'clock in the afternoon. Thank you. Hey.